Welcome. Hi, everyone. I'll be talking about the Large Area Survey Telescope. This talk might be familiar to some of you, but not all. Right, before I talk about the instrument itself, I'd like to introduce how this instrument came to be. We start with this measure of the grasp, which just kind of tells you what is the volume per unit time in which you can detect the standard candle. And this depends on many things, on limited magnitude, exposure time, dead time, and so on. I'll focus on two things. One is the effective area, and the other is the field of view. You see here that the dependency on the field of view is linear, while on the effective area is to the power of less than 1. Empirically, we know that the cost of a telescope depends on the effective area to the power of more than 1. So there's an important clue here. If you want to make a survey and let's say double the grasp, how do we do this? Well, if you do this via the effective area, then you have to more than double the effective area, and then the cost increases exponentially. Or we just double the field of view, and if you do this by just copying the telescope, building another one, then the cost is also linear, so everything is linear. So what this tells us is that if we want a high grasp survey, the most cost-effective way to do this is to just building many small telescopes. However, how small can they be? Well, for one, you want to avoid the diffraction limit. So in optical, you want an aperture more than 20 centimeters. But additionally, also, if you're making a small telescope with a large field of view, then our focal length will shorten, and this will hurt our resolution unless we decrease the pixel size. So an example, if you have a 30 centimeter f2 telescope, we want a 1 arcsecond resolution, we need 3 micron pixels. So there's a technological limitation here. For example, sub 4 micron pixels have only been on the market commercially since 2019. But so this is the origin of LAST, which is exactly a survey telescope that uses small telescopes for with a wide field of view and small pixel size. LAST uses these raster telescopes. These are 28 centimeter f2.2 telescopes with a camera that has 61 megapixels and 3.6 micron pixels. So this gives us together a pixel size of 1.25 arcseconds per pixel and 7.4 square degree per telescope. Now we can take, so this will look similar to some telescope you saw, but yes, we can take one such telescope, and we take it 4 times, and we put it in a mount, we point them in the divergent matter, and we have a field of view of about 30 square degrees. And now, of course, what we can do is take many of such mounts and put them together on one side. So this is the first node of LAST. Once constructed, it's being constructed in the Israeli Negev desert. Once it's constructed, it will have 70 telescopes, so 18 such 4 telescope mounts. It will have a field of view of more than 500 square degrees, and at the moment, 10 of such units are operational. Total estimated costs for hardware and construction is about $1.5 million, which is for such a site is really cheap. If you compare the grasp now against current and near future surveys, this is for 48 telescope, we see that it's fairly competitive in this measure. LSSD dominates by far, of course, just due to the depth. Grasp 10 times as high, but 1,000 times the cost. Some advantages and disadvantages of this kind of design. For one, it's of course, as we heard, also will go to, it's modularly scalable. A lot of these units components are off the shelf, so they're kind of cheap. If you wanted to, you could build your own LAST node in your own backyard. Failure points are usually isolated. So if one such unit breaks, you still have the others. You can still observe, you can still do your survey, and it's easy to modify. You can add filters, you can polarize this, and so on. And actually, at Bochum, the group of Anna Krowiak is using the LAST design to fit them with polarization filters. So you can make 4 different polarizations in each 4 telescopes at the same time and get your polarization angle instantaneously. Right. However, there's many failing points. There's a lot of telescope, a lot of focus cells, a lot of computers. So quite often something doesn't work quite right. So it's a lot of maintenance. But even more so, we have fairly large pixels for such small telescopes with fairly small pixel size. So with a lot of cameras, we're expecting the Senti telescope take about 24,000 images per hour, which will produce a data rate of 3.3 gigabits per second. So we'll need a very high efficiency procedure to reduce all the data and find all the interesting science in it. And this is actually a lot of our work goes into this procedure, but it's possible. All right, so last is a survey, so it's going to do a survey. It will scan the nominal survey strategy is to scan the sky in visits, whereas each visit is 20-second exposure images, where each of these 20 images are then co-added for a deeper image. Typical limiting magnitude for such a co-added image is about 21 magnitude. We're not using any filters, and we are operating in a B system, calibrated on Gaia. So with all these numerous telescopes and a large field of view, we will be able to scan the sky below MS of 2 almost 3 times per night, a bit less than that. And then our position currently covers a gap where there is no large sky survey at the moment. Yes, so science, it is primarily a transients finding machine. So most of the science is finding transients in survey mode, but also we do follow-up. We do gravitational waves and JVs and supernovae and so on. But also you can do cosmology for lensing, time delays. You can look for asteroids, comets. You can cell activity, anything that varies on short time scales will benefit from this survey. Transient detection, we do via subtraction. This is use the Zoggy method, same thing that ZDF uses. So an example, right? You have a reference image. You observed the sky a week ago. You save this image. You look tonight, and then you make the difference, and you see there's something new. So in the difference, you see in this case a supernova. Right, and yeah. So right now, what we see basically is that per night, we get about 1.7 of such transit candidates, 1 million of such transit candidates per night per telescope. So with 72 telescope, we expect more than 100 million candidates per night. Far majority of these are, of course, false positives, artifacts, fluctuations, and so on. So we need a good way of filtering this, and we employing a fully deterministic weighting process at the moment. So no machine learning, maybe in the future, probably in the future, but now we just not using it. And this is just a collection of hypothesis tests and heuristic methods, which will be published soon. But just an example of such a method, this is a statistic that we published last year. So the transients finding method is Zoggy. This is a statistics that checks for varying sources, basically. And we published the transient statistic, which checks for moving sources. So one of the common artifact error is that the images are not perfectly registered and they kind of move from one image to the other, and this looks like transient. So you can compare it to statistics and you can tell, is this more of a varying source or more of a moving source? And I'll say in the bottom right, you see left and right, is a residuals on varying stars and non-varying stars, and you see the population are different. So you can use this to distinguish the two scenarios. So we operate every night. We have a marshal where these are transits are into a reported TNS. So we also report these transits to TNS, and this is one of these such supernovae. You see that we cover this one, for example, fairly well in time. Right. to say on follow-up of large intensity areas, right? We have a large field of view. It's an older study, but using 12 units. If we test it against O3 gravitational wave alerts, then we see that in one, if we point our telescopes in different positions, then at one time we cover about 55% of the error region for the average alert. Where point one, we cover 70%. Point another time, 78. So we can cover all these large intensity areas very well. And then, right, so another thing, so our visits are 20 by 20 seconds. And of course, if a transient is bright enough, you will also detect them in the single 20 images. And we have this information and we save it. So in this case, you see a very rapidly rising and decaying transient. I don't know how well you can see it. In the lower right, there's a faint red object. So this is probably a M dwarf pair where you very well see when exploded and how well it rises and falls. And a note on this, some feedback from the community. So right now, these transients, CVs and M dwarf sphere and so on, that occur in the galaxy, we have them, but we're not reporting them anywhere. And something that in community we discussed at a previous conference is that Astro-COLIBRI can facilitate these kind of transients. And so we are also adding a functionality to report these to Astro-COLIBRI. And Fabian can comment on that if you like so later. But furthermore, LAST is not alone. It will be at the Weizmann Astrophysical Observatory together with its siblings, PAST and MAST. So we have LAST, PAST, and MAST. So LAST will do the clear photometry survey. PAST is also 4 telescope on one mount, but each with broad-band filters. So this will do color photometry. And then MAST is a multi-aperture spectroscope. So multiple telescope feeding into one spectrograph. And this will do spectroscopy. So this is a drone footage from at the LAST site at the moment. So we see the current LAST enclosure over here. These telescopes will be moved to the new one, which is larger and a bit more stable in its design. And this will house LAST and 2 PAST mounts, and then we'll have also for enclosures for MAST. So current status, we are finalizing these new enclosures for the 72 LAST telescopes plus PAST and MAST. We hope to have the full array next year. But in general, LAST right now is running from data taking to alert production. We get about 110 alerts per night, and in 1 year we published more than 1,000 TNS reports. We also do follow-up of transients in GCN and astronauts and so on. And so a summary, LAST is a under construction cost-effective optical survey. It will explore the sky at high cadence and a wide field of view. And it will be part of a larger facility with follow-up instruments, MAST and PAST. Thank you for listening. I'll just leave you some of the DP stack image from LAST.